you can see here on my screen right now, this is basically the view that I'm sharing of what we're going to cover today. So we're going to talk just a tiny bit about Python stuff, but we'll first start by introducing ourselves. So my name is Dave Whipp, and I'm the person who's responsible for the Geo-Python course that is registered in the bachelor's program of geosciences, and one of the two lecturers for this course. And I think we've been doing the course now for about 5 years or so, and it's slowly developed into a little bit bigger thing than what we anticipated at the beginning in terms of attracting a significant number of students, and also we now have a sort of team that's responsible for teaching the course. And my sort of partner, I suppose, in terms of delivering the lecture material is Vuokko, and maybe you can say something about yourself.
Yeah, so good morning again, everybody. So my name is Vuokko Heikinheimo. I'm a geographer here at the University of Helsinki at the Digital Geography Lab, and I'm responsible of the geographers part of this course, so the Geog 329 courses. Happy to see many of you here, hoping to get even more people on the live lesson. Looking forward to the course. We have 7 weeks now with the Geo-Python introducing you to the basics of programming. So looking forward to it. And maybe one other person to mention is Henrikki Tenkanen, who has been developing this course from the beginning. And he's also on the background supporting us with the materials and websites. And then we have 3 assistants helping you out with the exercises and anything that might come up. So I wonder if some of the assistants are here now this morning. Maybe Emil was there at least. So feel free to say hi.
I'm here. Hello. Hi everyone. My name is Emil Enström, reporting from home. I'm going to be the assistant on the Automating GIS course. So I'm also a geographer in my second master's year, and I did this course last year. I'm really happy to be assisting in this course. It's a really great course, so you're lucky to be here.
Great.
And
thanks,
I don't know.
Emil. Yeah.
Did you see Sonia or Alexi? Vuokko, I don't think I've seen them.
Yeah, not here, but you'll meet them on Thursdays and Fridays then.
Yes. So yeah, so that's our team, and I suppose I'm very clear-minded as always on these Wednesday mornings. I should just say that I'm an associate professor of geodynamic modeling, so I work in the Institute of Seismology in the department. So more of a geologist by training, and that's why I'm responsible for the geology part of, or the geology group in this Geo-Python course. All right, let's see now. Let's give you some other practical information. So I think by now you have probably all been to the course webpage. We sent out an email a few days ago about the course webpage, but if you've registered since then, it's possible you didn't see that. So we will be using this Geo-Python course page for the beginning, basically during the whole of period 1. So for the students in the Geo-Python course, for the geologists, that's the entire course will be on that page. Those continuing on to the second half from geography, the automating GIS processes, they have a separate web page for that. And I think we'll see the course page for our course soon enough, so I won't go there right now. But this is just mostly to tell you that everything that happens in the course here basically evolves around our course webpage. So all of the lesson materials are there, all the lecture videos will be there. If there are slides like the one that the ones we're looking at now, those will be posted there, as well as links to the exercises. So everything is more or less in one place. And as I mentioned, we'll take a look at that shortly. I suppose you know at least part of when we're meeting, and that is that you're here now. So our lectures will be Wednesdays at 9:15, and typically, although we would like to be done at 11:45, we might go closer to 12 o'clock. at least based on several years of observations. And in addition to the lectures, we have these work sessions. So these are basically to support you in working on the course exercises. They are optional, and they'll be held in Zoom at the same place. So same link that you use to join the lectures, you can use to join the exercise work sessions. And there's one on Thursday and one on Friday. And you can see the times here. In terms of which one you register for, it doesn't matter really if you've registered for one and go to the other, or if you go to neither of them, or if you go to both. It's mostly just to support you if you are having some difficulty working on the exercises. You can come there and the assistants will be available to answer questions and help with you working on the exercises. And we are going to be making one change to how the exercises work this year, that we're going to be suggesting you work in partners on some of the exercises. And so this might also be something that you will be coordinating with your partner, whether or not you attend one or the other exercise work sessions, so that you can be there together to get some help. But basically they're optional and you're free to go to whichever you please. And yeah, the question here in Slack about can you enter all the exercise sessions with the same Zoom link? Yes, that's right. I think we're just going to use one Zoom for everything in the course. We don't have any overlapping times, so it should be fine. Good question. Okay, maybe Walko, do you want to say something about the AutoGIS?
Yes, so a few words about the AutoGIS course. So this Geo-Python is part of it. So the first period is all about introducing you all to programming, data analysis, and visualization, so the basics. And that's worth 5 credits. And then some of you then might continue on to the second part, where we then start analyzing spatial data. So everything we do in this first period then helps you to continue in the second course, which is then more focused on actually automating the GIS processes. And then the second course has a bit bigger final exercise as well. So welcome. It's part of the geography master's program, but everybody interested is welcome to register also there. And if you have any questions, you can now post in the Slack chat box or ask me later.
Okay, thanks. So yeah, in addition to this Geo-Python course for the geologists, there was previously an Introduction to Quantitative Geology course that was given every year that you could follow up in period 2. That's now been moved to the master's level, and it will be every other year. So the next time it's taught is in 2021. So in case you're wondering what happened to that course, it has been bumped up to the master's level based on some student feedback and my observations, as well as then moved to being taught every second year. Okay, now it would be a good time for us to maybe get a little bit of information about who you are. We have some basic questions that we can ask you. We've normally done this class in a large kind of lecture room. So we've had the screen up in front of us where we could have you fill in some poll questions and everybody could see it. I think what I'll try to do is I'll have this visible on my screen with the poll results. You should be now able to go to this link and answer the first question about which course you are enrolled in. And I will pull up here the poll screen. Maybe I can see the responses, and maybe you can also now see the responses. And Walko, we have another question in Slack, or sorry, in chat. So we have the AutoGIS students surging ahead here in the polling results. I believe that there's a number of the geology students who are on a field course right now, so I'm hoping that's that's the case, and that's we'll have more showing up in the future. But perhaps for some of you, you can also see we have some students from Turku, some students attending from Aalto, and some who may not be enrolled in the course. at all, and that's fine. You're welcome to follow the course even if you're not enrolled. But if you want to be in one of these two courses and you aren't, and have some questions about that, you can let Walko or myself know. All right, so it seems like at least today, we are dominantly a group of the automating GIS processes students, and well, we'll see whether the group composition changes in future weeks, but at least now you guys can see a little bit of who's here. There's a few students from Geo-Python, and then some others from Turku and Aalto as well. Maybe we can go to the next polling question here. And so this should now be visible to you as well if you want to fill in your responses about how much programming experience you have. We've designed the course so that people with no programming experience whatsoever should be able to follow and complete the course. We try to approach everything as a sort of true introduction to both the Python programming language and programming itself. But it's maybe reassuring to know that there are some people here that have absolutely no programming experience, and you're not alone if you're one of those people. We have at least one self-proclaimed programming expert as well. So it looks like we've got 43 online, and it looks like we have got close to that number of responses here. So you can see clearly that some of us here have a little bit of programming experience, but it's either been a while or you just only have a little bit of experience. And some people can write some simple programs. Some have no experience whatsoever. So we've got a little bit of a variation in terms of who is here and how much experience they have. We do have a few experts in the house as well. All right, I think we maybe have one more question here about your experience. And this has to do with which programming languages you have used before. And yeah, I think this is not a big surprise. We've got people who've used R, and just about that same number have used a bit of Python before, so that's good. So you might have already some ideas about how things work in Python. Of course, Java is a popular one since that was the language of choice in the introductory computer science programming courses. I think that has now changed to Python as well. And a few JavaScript, some using C, C++, or C#, MATLAB, other, and none. So you can see again here we've got some varieties in terms of the experience. And if you have never used a programming language at all, don't panic. That's totally fine for this course, as we've mentioned. But everybody's going to have a little bit different background coming in, and we're actually going to try to take advantage of that in some ways to get you to work together so that some more experienced people can work with people who have less experience, and hopefully you can learn from each other that way. Okay, I think maybe we can also ask the question about your expectations for the course. So this is now a sort of you're free to fill in your responses here. So you can just type something in for what you would expect out of the Geo-Python course, and the kinds of things you would like to learn during this period. And this could be, anything that comes to mind when you think about what you would like to get from the course. I think you can actually vote on options too. So once someone has put in something, you can click on it and add your vote. Programming, of course, is something you would like to see here. Automating GIS. Okay, here we go. How to make lingonberry jam. I don't know how much detail we'll get into that on our lessons, but I too would like to know how to make lingonberry jam. Data types. So I'll let this go for a moment and just talk about the responses we can see here already. I mean, the basic Python programming, how to use it on spatial data, great. That is, you're in the right place for learning that, because that is basically the focus of this course, plus the part that continues on in automating GIS processes that shifts more to the spatial data. Here we focus on the basic Python programming. In some ways we deal with geographic or spatial data, but not in the way that you would in the second half of the course. As mentioned, the lingonberry jam, although it's number 2 in the voting right now for what you'd like to learn, maybe we can find some clever ways to work that in, but it's not currently part of the lessons. But learning to write simple codes using Python, yes, we're going to do that. Fundamentals of Python programming, data analysis, we'll do a bit of that, especially in weeks 5 and 6. We'll be doing some data analysis using a library called Pandas. And then we'll be dealing with a number of these different aspects. Having some practical examples and experience, yes, we're going to work with real data in this course. We will process data files and figure out ways to extract from those data files the things that we want to know, and make some connections, for instance, with programming and geography. Survival skills, maybe. We'll at least put some Python survival skills in your back pocket. And learning data types, we'll talk about that a bit as well, because for those who have had a little bit of experience with programming, there are things about data types that can be problematic, even though it's a very fundamental part of the experience of writing a program. So that's great. Thank you very much for your responses. It's nice to have some info about who we are as a group and the kinds of things that we would all like to learn in the course. And I think that many of them we will cover. Now, I think at this point, maybe I will also mention that we are going to have, as part of our first exercise, a similar set of questions to these. We have this information that you're giving us right now. This is anonymous, basically. As you can see, you just get a number and a bar, but we're going to ask you also to fill in some info about your past experiences, just so that when we try to pair up people for the exercises, we can have some ideas of who's who. And we'll get to that at the end of the lesson today. At this point, maybe I'll ask if there are any questions about what you expect from the course, or any other things in general about the difference between the Geo-Python and automating GIS processes. I mean, for period 1, we're together, we're the same group, we do exactly the same things. And in fact, the partners in some cases will be mixing between the 2 courses. So it's only for those who continue on to the second part of the automated GIS processes course that maybe you might be wondering whether or not that's for you or something. And you're welcome to ask in chat if you'd like. We can monitor that and answer any questions there. But perhaps for the moment, if there aren't any urgent questions, I'll continue on here with our introductory stuff and give you kind of an overview of what we're trying to do in this part of the course. So, as mentioned, we want to introduce the Python programming language, and truly we mean it as an introduction. We're going to introduce it, assuming you have no previous exposure to programming. And in that way, we're also going to develop your basic programming skills, as you can see here for point number 2. So it's really starting from zero experience. Along the way, we're going to also try to highlight some essential or some good programming practices that we feel you would need as a young scientist. Things related to topics as basic as picking good names for variables, but also different kinds of practices that will save you time and stress as you begin to use Python more and write your own programs. So those are the main kind of focuses for the course. And now I'm going to jump us over maybe to our course website. And you'll find much of the same information that we've gone through here. I'm going to give us a little bit of motivation for the course, or additional motivation for the course, in just a moment. But just to note that the basic course information on the course webpage, first off, the webpage looks like this, but the general information like when do we meet, who are the people, that stuff can be found under general information. You can find also learning goals for each lesson, and some information about how we'll do the grading, for example. We just use this number grading system, the standard 0 to 5 grading system. And in terms of how the grade breaks down, it'll be about 60% from weekly exercises and 40% from a final course project, which is kind of like a slightly extended exercise. And we'll talk more about that maybe when we get to explaining the exercise for today, or we can talk about it also in a subsequent lesson. But there's basic information there. I'm going to go here to lesson 1 for the motivation of the course. You're welcome to follow along just looking at my screen share, or you can look at your own screen if you would like. But to give you a little bit of motivation for the course, I think there's a few different things that we would like you to take away from the course. We would like you to learn how to program in the Python programming language, to learn the basics of how to write a simple Python program. But we also want to introduce ideas related to open science along the way. So we want you to know that when you're writing your programs, even though you're thinking you're writing something only for your own eyes and that you would use only for yourself, it turns out that if you've written something and you find it useful, there's a chance you're going to want to share it with someone. So it's worthwhile to write your programs from the start in a way that is easy to understand and easy to share. So we're going to emphasize that along the way, some tips about how to make your programs easy to understand. We'll also introduce you to ways to keep track of the changes you make to your programs, because one of the experiences that I certainly had as a PhD student, and occasionally still have now, and I'm sure Vuokko has also had the same experience, is you've written some piece of software or written a small program that was working, you make some changes and it breaks and you can't remember what you changed that broke it. So we'll introduce you to a way of keeping track of the changes you make to your programs. This is something called version control. And essentially, if you build this into the way that you work, you basically keep track of every time you make a change. And if anything breaks, you can always go back. We're going to also introduce the ideas of writing programs that are going to make sure your science is reproducible. This is something that's increasingly important and emphasized in the open science community, is that when you want to publish your results somewhere, more and more, even if it's in your sort of master's thesis, it's a great idea to have whatever program you use to generate your results available so that if someone wants to reproduce your results, they can do it. It's a very open way to do things, to say, here's my program, go ahead and do what I've plotted. Go ahead and reproduce my results. It also keeps you, keeps you honest in a way. You're not just kind of hiding things, not that any of you would, but this is the reason why it's being emphasized. And also, we'll talk about producing some data visualizations that are simple and effective. And we're only going to introduce the topic, but you'll go into that in more detail as you continue on. So with that idea in mind about these data visualizations, let's just take a quick look at an example. Now, this is what a typical data file would look like that you might encounter, that you would want to visualize some data out of here. So this is a global temperature data file, and this is just the first 30 lines out of it. I think in total, it's probably something like 10,000 lines long. But looking at this, I would be very surprised if any of you learned very much from this data file itself. There's data here, But the issue is that the raw data itself isn't very insightful, isn't inspiring, doesn't kind of immediately tell you about what it is. It's just raw data. So in order to get something out of it, we need to find a way to manipulate this data to make it more engaging, to make it more accessible, so that people who look at the data have to do less to understand what's in here. And this, as it is right now, I mean, it might as well be random characters. It has almost no meaning, and there's not an interesting story that you can see here. But there could be an interesting story in the data. We just can't see it. So one way that we could illustrate the power of this data would be that we could plot it. And we could plot it, for instance, in an XY plot. So here, this is an example of something that would be derived from a data file like the one we were just looking at. That's now showing from 1880 up until about 2015, I think in this case, or maybe 2011 actually. The deviation in the mean annual temperature from the temperature calculated of the period from 1901 to 2000. So in the year 1880, for instance, it was colder than the average between 1901 and 2000. And looking at this, all of a sudden we can see much more information about what this data is describing. We can see, for instance, that there was a period of time when temperatures were a little bit cooler than average. They went up to around average in sort of 1940s and really continued up until about 1970. But since 1970, temperatures have been increasing significantly, such that globally now, the average temperatures have this anomaly or sort of anomalous value of about half a degree above the mean. And you can see here also these uncertainty bars that say that this is a significant deviation from the average temperature that was calculated. We've unlocked a lot more information about the data that we have by plotting it in this way. And now already you could show this plot to someone and they would start to get the picture relatively quickly. There's one drawback with this. And the drawback here is that we have this global temperature data, but we have nothing spatial about it. There's no connection between this temperature data and the location where these temperatures have been measured. So this is an improvement, but we can do perhaps even better. So we could look at our data again, same basic data files, but looking at things now in a different view, here in a sort of more spatial format by looking at these temperature anomalies globally, but now connecting our temperature anomalies to the locations, the geographic locations where these anomalies have been observed. And so this is data from January 2020. For those of you who might remember, I know 2020 feels like it's been several years in itself, but if you can remember all the way back to January, you might recall that we had rather disappointing winter weather. And you can see here, for instance, that the edge of southern Finland is squarely in this very dark red region of anomalously high temperatures. Temperatures that in this case were in excess of 5 degrees above the average temperature for January from 1981 to 2010. So now we have a different kind of view of the same data. And this is also very interesting because now we can see not only how the temperatures have varied, but how they have varied across the globe. And in some places, how temperature has basically not been anomalously warm or cold, but in other regions, such as in much of Russia and as well as southern Finland, we had anomalously high temperatures during January of 2020. So this is, again, much more engaging and interesting way to look at the data. What we have sacrificed with this view is that we've lost our time series component. So we have space now, we can see how our temperatures vary across the globe, but we've lost our component of how these vary with time. And so to do both of them, spatial and temporal variations in something like temperature, we're going to need a really unique kind of visualization. And just want to show a couple examples of these kinds of visualizations that are available that you can find online, for example, that have been generated using Python and essentially by processing data files just like the one we looked at the start of this little motivation section. So here we have temperature anomalies by country, and maybe I can make this full screen. I hope this doesn't like break Zoom or something. Okay, maybe you can see that now. So I can't remember what this was called, like a pill plot or something like that. But you can see here now the names of all these different countries. They're listed alphabetically, so you don't quite have a sort of spatial view, but you do have a spatial connection in that you have the names of the countries here. And we have now the year up at the top and the anomaly in terms of the temperature, deviation from the average, is shown either as red when it's warmer than average, blue when it's colder than average, and the size of the pill will show you the magnitude of that variation. So this is an animation. You can just click play here. And now we can watch to see a few different things. We can see our spatial data, but we can also see how things are changing with time. So you're getting here sort of a muted colors, maybe a slight orange, but you're still getting the blues in there. There was a blue year. But as we go forward in time into the 70s now, you remember that we globally saw temperatures were starting to increase in the 70s and 80s, and now we start to see more and more of these kind of reds and orange colors, such that by the time we get to 2017 in this case, my bars, my little zoom bars covering things up here, we can see that basically everywhere we're having globally positive anomalies in terms of temperatures, and in some places those anomalous temperatures are quite significant. Plus 2.4 degrees in Mongolia, for instance, is a pretty significant temperature anomaly. So that's cool. Now we have space and time in the same kind of animation. And just to show you one more, this was also done using Python. In fact, if you're clever and go looking around online, you can find the source code for generating some of these animations. And you might even, by the end of the course, have some idea of how to understand that and even modify if you were interested. But this is, again, a sort of type of visualization of the same type of data we just looked at, deviations from the average temperature. And now you can see in the sort of ring going around the outside of this plot, the names of different countries, here clustered now by which continent they're on. So you can see here countries in Europe, and as you go around different places, you can see different groups of countries that are clumped together, and you can also see the labels on the inside there. Now with this one, I'm going to hit play again. We're going to see the lengths of the bars indicating our temperature deviations, and you can see the year, of course, in the middle. And here, I think, is also an interesting view to see spatially how different regions were maybe warmer or cooler than others. But again, you see the same general trend that as you get into the years like 2018 here, for instance, we're now going to move to a sort of forecast of how these temperatures are expected to increase globally up until the year 2100. This is probably somewhat alarming because in some of these cases, the temperature, here we have our variations up in the top from 1900 up to basically, I think, 2010 or 2012. And you can see that, the maximum positive anomaly was this sort of slightly orange color. And as it go forward in time, at least based on this prediction, these temperature anomalies would be quite high. And we could try and find Finland's bar here and say that we'd be looking at most likely temperature anomalies that are +3, +4 degrees C, which means bad things in terms of the hopes of cross-country skiing in southern Finland, for sure. So the point here is that this is basically ways to engage people that are based on visualizing data that's processed with Python and visualized using Python tools. And so we're not going to say by the end of the course that you will generate this kind of animation with your own source code. You'll just type it out, and by the end of the course, you'll have this thing. But we'll get part of the way there. We'll get to the point that we can process and read in data files, we can manipulate them, and we can visualize the output, including doing things like animations of temperature anomalies. So we can do a simple form of that, crafting out a making a visualization like the one that's shown here, for instance, or the same with the pill plot animation. That takes a little bit more experience with Python, and it's got a sort of a bit of an artistic element to it as well. And so, as mentioned, you'll get part of the way there, but it may take you a little bit more time before you're ready to put out your own climate change animations online. But this stuff is cool. I mean, you see these animations pop up, for instance, on Twitter from time to time, and sometimes they really spread quite widely and engage a lot of people because it's intuitive. You look at it and you understand what the data are in the visualization. So yeah, that's I think the kind of motivation, or hopefully something that will motivate you a bit in terms of what we're going to cover in the course. And I'm going to jump back from the course webpage to our slides here. And again, if you have any questions at this point, I would suggest posting them to Slack. I can see, or sorry, to chat. I can see the chat off screen here, and would be happy to answer questions, or Vocal can also answer if she sees a question. So I'm going to continue now. I think we'll go for a little bit here with our introductory stuff, and then maybe we'll take a break and then jump to some more practical things for today, and some other practical things related to the course. But what I want to do here in the next little bit is just introduce some basic ideas about computing, basic ideas about programming, and just sort of set the stage for how we can think about interacting with the computer. And so talk a little bit about computing practices, what is a computer, and what's a programming language, and then also look at the kind of components that go into writing a computer program. And we'll do this somewhat quickly because you can refer back to these slides later if you would like, but this is good stuff to at least touch on here in the beginning of the course. And one of the first things that's, I think we've already made the point to say, is that, programming skills, in my view at this point, programming skills are sort of an essential piece of being a young scientific person. So whether you go on to study more and go sort of looking for an academic pathway, or whether you go to working in the private industry or doing anything else, you're going to be approaching problems like interacting with data as a scientist, and this is one of your essential skills, is to have basic programming skills. And we know that you're not computer scientists. I mean, at least I think most of you are not computer scientists. I'm not a computer scientist. Woko is not a computer scientist. But it doesn't mean we can't program. It doesn't mean we can't learn to interact with the computer. And our focus here is to take some small steps to get started and to learn together. And yeah, I think you absolutely should learn how to program. Why would you want to do that? Well, I can say less about the sort of geography side, but certainly within geology and the geosciences in general, there's an increasing focus on more and more quantitative analysis of data sets, using simple numerical models to understand what your field data tell you, what your laboratory data tell you, and all of these focus around the idea of at least having some basic programming skills. By having those basic skills, you can essentially unlock a whole set of things that you can do to be able to get more out of the data that you have, and explore things on a sort of deeper level, and it makes you a better scientist. Another reason you might like to program is that you can take software that already exists. You could find, for instance, Python programs that are on various websites where you can go and you can download the software, and you can look through it, understand not only what the software is doing, but you can even start to make changes. You can extend what the software can do. And if you find something where, you know, a piece of software has a Python interface to it, like many of these software packages, ArcGIS, QGIS, the ParaView software for doing 3D data visualization, Google Earth, many of them have the possibility of using Python to interact with the program. And all of a sudden you can extend it to do things that it couldn't do before that help you interact with the data that you're interested in using. So I think that's also something that's quite useful about learning the program, in particular in Python, because Python is fairly widely used for many of these geographic software packages, as you can see, for instance, right here. So this is the Python console in QGIS. I think Wolfel probably sent me this image, and I don't remember exactly what it is here. But the point is that here you have loaded some data into QGIS. You can obviously see our geographic location is the Helsinki metropolitan area. And down here, you have a Python console where you're typing commands in to interact with the data that is visualized within QGIS. And so you can start to do some pretty cool stuff by making little scripts that can go through and interact with different elements of what you've loaded in a data file, for instance, in QGIS. And it might be somewhat hard to sell some of you on the idea, but I think programming is actually pretty fun. So, you know, you see more and more that there are these kind of kid-oriented programming books that are being put out where they're wanting to introduce young, like primary school age kids to programming, because it is fun to take a complex program and break it down into little pieces. To think about, you know, I ultimately want to get this kind of visualization of my data. What are the steps I need to take to get there? How do I need to sort of interact with this data file to get out of it the visualization that I really want? And so this can be kind of a fun experience to try and think about, okay, what are the steps that I put together? And how am I going to solve the problem? What do I do to test it? And how do I make sure that my solution is actually right? Just because my code works without any bugs doesn't necessarily mean my solution is correct. And so this can be a fun little process to sort of separate things and break it down to the basic elements, and can be very exciting and rewarding, if you can believe that. Of course, I have here when the code works. It can also be quite frustrating, as you folks will probably experience at some point during this course. So now I just want to say a couple things about the sort of scientific method. I guess maybe you've seen the scientific method in some form previously, but I want to highlight ways in which a little bit of basic programming can make you a better scientist. So the general scientific method is here, these kind of 8 steps about defining some question, getting some information about that, finding some hypothesis you want to test that you think explains the data, then testing your hypothesis, analyzing the data from your test, doing some interpretations, publishing your results, and retesting. This is the kind of overview of the standard process of doing science. With a little bit of programming, we can improve a number of these steps. So for instance, gathering information and resources, collecting our data. If we have a simple code to read in large numbers of data files and handle that large volume of data efficiently, that's something that's going to be quite useful, because, you know, for instance, loading 10,000 line data files into Excel one by one is a quite tedious process. With a small Python program, you could basically take that down to being something quite simple. Testing a hypothesis and performing an experiment. Of course, I've highlighted here performing an experiment and collecting data, again, because if you write some simple programs, you can find ways to automate and make the process more efficient. Analyzing the data, of course, we'll do some data analysis in weeks 5 and 6, again, using this pandas library, where you can take a very complicated data set and distill it down to things that are much easier to understand. And interpreting the data really in terms of doing visualizations and, again, simplifying what you're looking at is also something that a little bit of programming can help us with. if we learn also along the way, not only the programming, but some good programming practices, we can help ourselves in making sure that when we do our experiments, we do them in a reproducible way. And this is something we'll try to build into the course from the start here. Also with the idea that we want to have people be able to retest, reproduce our results, redo the things that we've done to make sure that what we've done is correct and that the person understands. I mean, just in the same way that when you have some nice looking result and you're a little bit suspicious of it, you kind of want to know, okay, how did this person get to this result? And there are some good programming practices that can help us say, oh, you want to know how I did this? Here you go, you can do it too. Okay, so that's the kind of introductory stuff. Now I want to talk a little bit about computers, computer programs for just a few minutes. And for this, I'd like to again ask you to give us a little bit of information. Maybe if Walko is around, maybe could help with, yes, putting up our next quiz question or polling question about what is a computer. I will just jump back here for a second so you can see the website again. So we're just going to the geopython.github.io/poll. And you can fill in, again, like we did before, your responses, and you can also vote on the responses that have already been filled in there for what you think a computer is. And I'll give you a few minutes to fill in your responses. All right, so we're getting some set of responses filled in here. This looks good. Lots of good ideas about what is a computer. So the top one right now is a machine that performs logical and mathematical operations. That is part of the definition of a computer for sure. And we will perform some logical and mathematical operations using the computer as part of this course. And the computer here, hardware and software, I would say, in a sense, yes. It's the equipment itself plus the software that is used to operate and make the computer do things. So yes, that would also be part of the definition of a computer. Calculator is an interesting question of whether you call that a computer or not. It really depends. If it's a kind of graphing calculator where you can write programs that would modify what the calculator does, in some ways you could call that a computer. A sort of standard calculator where you just type in the keys there and it has a predefined set of things it can do, strictly speaking, wouldn't necessarily be a computer because you don't have a program that you can modify to change what the calculator is doing. So that's a little bit of a tricky one. Depends on what kind of calculator, perhaps. But again, yeah, here, memory, processor, input device, output device, that's certainly the hardware part of a computer. And my only true friend, well, that's possibly true as well. I don't know if it's part of the definition of a computer, but it may be to you. And you can see, of course, here some other ideas as well. The one that jumped out to me is a gaming console with a question mark. Yeah, I would say gaming console is a computer because it has a processor, it has a storage device, and it has modifiable software that changes how the gaming console operates. And so when there's some update to the gaming console's operating system or whatever, then there might be new things that get, new features that get added, or whatever the case might be. So yes, thanks. Very good set of responses once again. Here's the definition of a computer according to a computer scientist. And so this is a machine that stores and manipulates information under the control of a changeable program. You can see here input devices, output devices, CPU, memory, many of the things that we just had in our definitions. Just to highlight a couple things here, manipulates information. So that suggests that there would be some input and there would be some output. So you feed in some information, the computer does something, and it puts out something that's been modified to either be more useful, new, different, whatever. But it actually does something. It doesn't just take the same information and spit out the same thing that you just typed in. It does modify things. In the changeable program part, that's what makes a calculator, for instance, different from a computer, if we're talking about the kind of standard, a regular basic calculator. In this way, in this same definition, if I have my smartphone is certainly qualifying as a computer. It's a machine. It stores and manipulates information. When I tap things on the screen, I interact with it, and it gives me different information coming out. And certainly it has a changeable program in that the operating system for the phone can also be updated. So that's our basic definition for the computer. We can talk now a little bit about what they're good at. So computers are good at well-defined and clear tasks. So if you tell the computer add 2 plus 2 and return the answer, for instance, that's what's shown over here on the left in Python programming language, it can do that. So we got a function here called print that has a very specific definition for what it should do. And then we'd say print 2 plus 2, and it writes back out to the screen value of 4. Or we could print some characters here and then say 2 plus 2 equals, and then have it add 2 plus 2 to say 2 plus 2 equals 4. That would be shown on the screen. So it's good at well-defined tasks, storing data and manipulating data, repetitive calculations. Certainly that's something that computers are good at, and we'll put them to use doing repetitive calculations in some ways. And processing data or instructions. These are all things that computers are well designed to handle. What they aren't so good at are poorly defined or abstract tasks. So you can find ways to interact with computers now. There's ways in which you can use different types of learning methods in the computers to give them less clear instructions and have the computer start guessing at what you want it to do. But in general, that's a time-intensive and sort of computing expensive task. So if you give the computer an abstract task, like just tell the computer, calculate pi, most probably it won't know what you actually want to do. And it's not that the computer can't calculate the value of pi, it's just the task, calculate pi, is not clear. It's not like 2 plus 2 equals 4. The computer would say, well, it probably would just give you some error message. But essentially what it's looking for is a clear explanation for how it should calculate pi. It's not a problem. Here's the first 1,000 digits of pi, and you can easily find codes that will print out many more digits of pi than this. But so the basic idea is not a challenge of can it do this, it's just it needs to know a specific way to do that calculation. And there are, in some cases, problems that just can't be solved by a computer because they're too big. So this is the SISU supercomputer, and this is one of the CSC, the supercomputing group in Finland's older computer clusters. It's big, 40,000 processor cores, about 107,000 gigabytes of RAM. So it's a pretty powerful computer, but still you can find problems. Like if you say, I want to run a global climate model for the last 500 years at a 1 meter resolution. That's going to be a problem that's just too large for the computer to be able to to store in memory. So that is to say that there are still cases where you could find problems that are just simply not solvable by a computer. Unfortunately, Sisu is now deceased. It was decommissioned last year. And anyway, I just like the picture because I think this is a really nice looking image of the Northern Lights on the computer cluster. Otherwise, most of the time, computer clusters look pretty, well, they're not very interesting. Okay, so we know some ideas now of what computers can do, what they can't do, what they do well. What's a program? Here's a couple examples of programs. This is an old school Fortran punch card where you would, punch out different spots on this card and feed it into the machine that would read that in and interpret that as a program and do some stuff. Or here's an example of a Python code doing some other things. We don't need to worry about what this is doing. But in both cases, we have a set of step-by-step instructions of telling the computer exactly what to do. Again, we can't say calculate pi. We got to say, how do you calculate pi? First, do this, then do this, then do this, then do that. If you give the computer detailed instructions of what to do step by step, most likely it will be able to do that as long as it's a solvable problem. And we can modify the program. And when we do that, we expect that the computer will then do something slightly different. And just for terminology, the word software is basically just another name for a program. Probably you already had some idea what a program was. Programming language is just our way in which we want to talk to the computer. So how we interact with the computer is to talk or write things into a format that the computer can understand. So our native languages, speaking to the computer, certainly you can do certain things, like I can tell my phone, Siri, tell me what time it is or whatever. And it understands some parts of my spoken language, but I can't, I don't know that I could ask Siri to calculate pi. Maybe that would work. But there's lots of other things, like I couldn't say, go download these data files and make me a nice visualization, at least not yet. So our programming language is basically our code or the instructions that the computer understands to do the things that we want to do. So that's exact and unambiguous. So again, you can't have a functional programming language that has uncertainty about what something means. If you type in print and the computer's like, do you mean to do this or do something else? That's no good. It has to be clear what each thing does. And so that's why there's a precise form, a syntax. So for instance, the print statement, it is the word print, P-R-I-N-T. If you put in something else, it doesn't have the same meaning. And a precise meaning, in this case, print would mean to display something on the screen. And Python is just one of many different kinds of programming languages. Now, I think we maybe have a break coming up here soon. I'll go over this, the rest of this stuff about developing a program here a bit briefly, but just to give you some ideas that there is a bit of a sort of set of steps you can think about when you want to start writing your own little piece of software. At this stage, since we haven't actually done anything in Python, it's probably not worth spending a lot of time for us to go through and look at this in detail. But I'll go over this kind of quickly just so you have some ideas about this sort of general strategy. So you can see here these 6 steps: analyzing the problem, determining specifications, create a design, implement the design, test it, and then maintain if necessary. And we can think about this as a nice example. So as you may know or may be able to tell from my accent, I'm an American and was raised in a country that is still using Fahrenheit for temperatures. What that means is that 70 degrees Fahrenheit is a nice temperature, in my opinion. 90 degrees Fahrenheit is hot, and water freezes at 32 degrees Fahrenheit. It's very intuitive. So we have these temperatures here. That's what's in my head for what I see as comfortable. The problem is here, when I go look at the news, or if I go to the FMI website to look for what the temperature is going to be for the day, of course, I get temperatures in degrees Celsius. So what I would like to do is I would like to know what I can do in terms of wearing the right clothing to work or being prepared for the day based on something where I have temperatures in degrees Celsius. And I think a simple program might be able to help with that. So first off, I need to analyze the problem. Before we go on to solving it, I need to know what the issue is. And in this case, the problem for me is that I need to know what the temperature means in Fahrenheit so I can understand when I hear a temperature in Celsius, or vice versa. So then I need to determine the specifications. In the example of this temperature conversion thing, my specifications might be that I'm going to have an input temperature. My input temperature could be Celsius or Fahrenheit, and my output temperature should then be either Fahrenheit or Celsius. So I can convert between the two. And those would be sort of my specifications. Then I would make some design, so my overall structure of the program. And this is something you can often even write out just on a piece of paper as what's called pseudocode. So you don't write in the Python programming language, but you just write it out kind of line by line what you're going to need to do. So, first read in the temperature in Celsius, then convert the temperature from Celsius to Fahrenheit, and then finally print the temperature in Fahrenheit out to the screen so the dumb American guy can figure out what clothing to put on. Something like that. After that, we're going to implement the design. What does that mean? Well, that means that we could take our pseudocode where we've written out the sort of steps we think we need to take and convert that into our programming language. So we're going to translate that into Python. And if we have already the pseudocode, the script of the steps, converting it to Python, once you know the syntax a little bit, once you know some of the terms and the things to use to get the program to do what you want, that step is not really necessarily a difficult one. It's actually the pseudocode and those steps before that take more thought than, for instance, implementing the design. So if you do most of the thinking here, step 4 can be quite straightforward. After that, we should do some testing. So once we have a functioning program, once we've gotten all the syntax errors solved and things like that, we can now test it. So one way to test things would be to say, okay, well, let's choose some values that I know. I know that water freezes at 32 degrees Fahrenheit, and that's the same as 0 degrees Celsius. So if I put in 0 degrees Celsius to my program, I should expect to see that the temperature in Fahrenheit is 32 degrees Fahrenheit. If my code doesn't do that, then there's a problem. And so we need to know what these correct values are. And if I want to test 1, that's fine. So 0 degrees Celsius, 32 degrees Fahrenheit, that's a good one. We could also check the boiling point of water. So we know water boils at 100 degrees Celsius, 212 degrees Fahrenheit, again, very intuitive. So we should be able to take our program and put in 100 degrees Celsius and have it return to me 212 degrees Fahrenheit to know that it's working. And you can think about other cases. Oh, what if I put in a negative temperature? Okay, if I put in a negative temperature, do I get the expected value that comes out of my program? So those are the ways in which you can think about testing things. And that's a very important step because, again, the code might put out some temperatures in Celsius, and who knows, if I don't know anything about the temperature in Celsius, I could be addressing for completely wrong conditions if my code doesn't work the way it's supposed to. And then after that, if there's a step that's necessary to maintain the program, that's a useful thing to do as well. If we want to have something that you think, hey, this is kind of cool, maybe someone else would want to use it, you may want to share it, in which case you may then also need to think about, okay, if something my program depends on changes, do I need to make changes to the program to make sure it still works? So those are the kind of very quick introduction to these steps for making some programs. We talked about what a computer is. This is our device that's going to process information. It's going to take input, do something to it, and give us an output value. And it's controlled by a program that can be changed, which is what separates it from being, for instance, a calculator. Our changeable software is a key component of what we would call a computer. And there could be, storage devices and other hardware pieces in there, but the essential idea is input, something happens to the input, in a form of processing and output that comes out that's different from before. And what happens is something we can control. Our program is basically our list of instructions. It's almost like a recipe. It tells us step by step what to do, and it's exact. It's clear to the computer what to do at each step, so there's no uncertainty, and that will allow us to do our data processing, for example. And we've gone through the steps of developing a program, so I don't think I will go any more. I don't think I'll say anything more about that. At this point, I think it would be a good time for us to take a little break. Why don't we take maybe 10 minutes or so? Or let's call it 12 minutes. Let's come back at 10:35, and then we'll continue at 10:35 with the rest of the lesson for today. Okay, so yeah, see you folks back here in about 12 minutes or 11, whatever. All right, see you shortly.